Thanks. Let's begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you again, Lord, for these students. I just pray that you just be with us today as we study your creation, Lord, that you give us understanding. And I just pray, Lord, that you be glorified, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Excuse me. So most of you haven't really worked that hard on the homework yet since it's not due tomorrow. And, I mean, it's a fact. But it's not a good fact, but it's a fact. And so, not in response to that, but also just because of generic scheduling, I'm going to use Monday for your questions, which means that the homework will be due Tuesday. So, just so you know. So today, of course, I'm going to cover material. In particular, we are going to cover some of these things. All right, so let's get started. Green's theorem for a region with a hole. So let's remember what did Green's theorem say? It said that the double integral over some region R of partial q, partial x minus partial p, partial y dA was equal to the integral around the boundary of the region, counterclockwise oriented, of p dx plus q dy. Now we called this the divergence, the curl form of Green's theorem last time. Was that anywhere near? Almost. I didn't think so. Okay, so the important thing to notice here is that R looks something like this. I mean, R could look like all kinds of crazy nonsense, but there was one thing that's true about R, is that R had no hole. All right? You could, in principle, deform the boundary of the region R to a point without getting snagged on anything that wasn't in the region. It's a simply connected set. That was our assumption. Now, what would happen then, so let's consider a new thing. I don't know, whatever. Let's call this thing D. And now there's some hole inside of it, all right? So the actual, man, I really wish I had a chalkboard. This is stupid. Sorry. Every once in a while it weighs on me. We should have chalkboards. Get out. Sorry. Sorry. I'll behave. So the boundary of D now has two pieces, right? The boundary of D has two pieces now. So the boundary of D has, let's say, C1 union with C2. Or maybe I should say C in and C out. In, out, right? And we insist then, this is a rule, the boundary of D must be given a positive orientation. That's our default. When I write the symbol partial D, what that's saying is, look at the positively oriented edge of D. Timothy, if you want to move up to your usual spot, you don't have to sit back there. It won't disturb me. Can you see? Okay. A little bit. I'll survive. It's okay. So the idea of a positively oriented boundary is if you imagine yourself, oh man, I wish I had a Lego man. Anybody got a Lego man on them? Nobody's carrying a Lego man today. It'll take me 5 minutes to get to my office and back, though. But I do have Lego men there. That's true. Make Tim go. No, I will use my thing. I will imagine that this is a little man. All right, as he's walking, the surface, the inside of the surface should be on his left. So that means the outer edge has to be oriented in this way, right? Okay, you see that? That's counterclockwise. for the outer edge. See, it's on his left. Now, on the inside, if he walked counterclockwise, the hole would be on his left, right? So the positive orientation for the inside is the opposite way. Let's see here. So you got to go clockwise on the inside hole in order to keep the inside of D on the left as you go around it, right? So again, inside, clockwise, outside, counterclockwise, all right? So far, so good? We'd like to come up with an analog of Green's theorem on this shape. So what we know Green's theorem for simply connected shapes. Can you see how to take this and to break it into two simply connected shapes? What do you do? Yeah, cut it in half. That's exactly it. So if we just pick a place to cut it, how about here and there, right? Then if you look at it, let me shade the upper piece with, say, a little bit of green here. This is simply connected, right? And it's got this. So I need to come up with a name for the, let's say that this is C out, the north piece, all right? So you have the north piece of the out, and down here, we'll say we have the outer piece, the south piece, right? Then there are these cross cuts. So I'm going to draw them as if they're different, but they're, of course, the same. So the green one, we're going to say goes like this, all right? And then let me use red for the opposite, the reversal of those. These are actually the same line. I'm just drawing them separate so you can see them both. The opposite direction, all right? So let's call this, I need some other names. Let's call this C1, C2 for the red, and the green I'll call C3 and C4. You guys with me? So if you look at this, if you look at C out, the north piece, unioned with, C4, unioned with, oh, I need a name for this inner piece too, don't I? What's this? This is C in, the north piece of that. Union with C in, the north piece of the inner curve. Union with C3, this is the boundary of the north piece of the region, let's say. And that's a counterclockwise. That's a counterclockwise oriented boundary of the simply connected northern piece of this kind of weirdly shaped annulus. And likewise, so here is C in, the south piece, right? As you can see on the other side, when I'm about to foolishly try to shade with a marker on a whiteboard, and there's the answer to your question, sir. Why chalkboards are superior is because you can do this thing called shading on them. Can you shade on a? I cannot shade on a whiteboard. I mean, pathetic. Sorry. The boundary of the south piece of D is going to be the outer piece, C out south, union with C2, union with what? Oh yeah, I'm sorry. Union with CN. Well, it's weirding me out because I'm going around it in the reverse order. Union with C1. So I mean, it's easier if you start like C1, start here. C1 goes like that. Then C in south goes like that. Then C2 goes here, and then the southern piece of C out goes all the way around the bottom edge. So we're back to where we started in this simply connected southern piece of the domain. Yeah.
I notice now that you've cut it in half, boundaries now go clockwise.
Yes. Isn't that weird? I mean, that's convenient, though, because now I have a boundary of two regions, and the boundary is counterclockwise oriented, which means I can apply the standard version of Green's theorem to these pieces. And there's something else I want to notice before I do that, though. It's that if you look at the integral of a vector field, f dot dr along C2, it's equal to minus the integral along C4 of the vector field dot dr, right? And likewise for C1 and C3, right? Because, why? Because C4 is equal to minus C2 and C3 is equal to minus C1. They're reversals, right? And we know if we reverse the curve, the line integral changes by a sign. So what I'm really trying to tell you is I can add the line integral along those crosscuts. I can add in the line integrals of the union of C2, C4, C1, and C3 without adding anything. That's just adding 0 if I add those line integrals, because it's just adding 0, really. So that's important. Excuse me. So let's start with the integral around the boundary of D of, let's say p dx plus q dy. Well, that's the integral around the boundary of the southern piece of p dx plus q dy, plus the integral around the boundary of the northern piece of p dx plus q dy. You'd say, wait a minute, though. That's not the same boundary. You added in those green and red crosscuts. Isn't that adding something? No, it's not, because those cancel out to 0. I haven't added anything by adding those in. And yet I have, because now I can apply Green's theorem to both of those separately. And what do I have? The southern piece, And then, of course, using the additivity of the double integral, if I integrate a function over two regions, if I take the union of those two regions, it's the same as just integrating over the entire region, right? Because the integral's additive in that sense. So I just can say that's the double integral over D of partial q partial x minus partial p partial y dA. Which says Green's theorem still holds for regions with holes, right? Yeah, you have to know where the hole is. And what's the other rule? You got to be careful. We have to make sure we orient the hole in the right way. The hole has to be oriented in the clockwise sense. So there's a corollary to this theorem, right? If the region looks like this, so say the outside is C1 and say the inside is C2, and suppose that both the outside and the inside, and here's D, suppose the outside and the inside are both, C1 and C2 are both counterclockwise oriented, all right? So in other words, I'm deliberately not orienting the inside one clockwise. Then we get the corresponding result that the integral along C1 of p dx plus q dy minus the integral along C2 of p dx plus q dy is equal to the double integral over D of partial q partial x minus partial p partial y dA. Notice both C1 and C2 are counterclockwise oriented in this scenario. Do you see why that's a corollary? You just use what I just proved and use the fact that, you know, the integral around the boundary of D, as it's positively oriented, okay, so the, you know, part of that would be the clockwise oriented inside. So if I reverse that, then I get counterclockwise, but that brings out a minus, hence the theorem. Yes, sir? Well, up here, it was the sum of the integral around the inside, around the integral. I mean, here, this would be, I mean, this is in some sense, okay, so this is like C1, this is like minus C2. Oh, wait a minute. Well, that's not quite right. Sorry, that's total nonsense. Excuse me, wrong analogy. So, I mean, the boundary of D has two pieces, right? The outside counterclockwise, the inside clockwise. So if I, you know, so I can write the integral of the boundary of D as equal to the integral over the outside plus the integral over the inside. But this is clockwise, counterclockwise, and this is clockwise in the original setup. So if I switch this to counterclockwise, that brings out a minus.
Right. Okay. So I was just trying to figure out why the double integral did not have any difference from the last one, but it's the line integral.
Yes. Because I'm still just using the theorem. It's just I've not respected the rules of the theorem, which is that the inside has to be clockwise oriented. And that's why there's a minus rather than an addition.
Clarify what you mean by, okay, so C1 and C2 over there aren't related to C1 and C2 here.
No, these are different. I mean, here, I'll put a tilde on it. Ooh, there. There's yet another corollary to get from this, corollary number 2, aka the deformation theorem. States the following: if Qx is equal to Py inside D, which is bounded by C1 and C2, like we were just picturing, both counterclockwise. I mean, they could both be, actually, honestly, they could both be clockwise, and this would also be true, as we'll see why in just a second. But what happens if Qx is equal to Py inside D, which is, you know, this in-between region here, right? This annulus kind of thing. Of course, you could pinch the annulus, right? I mean, you could also have something like, there's nothing really stopping you from having this situation either, right? I mean, well, let me shut up. Goodness gracious. Then what can we say about the integral of C1 and integral of C2? See? Because if this is 0, then the integral of C1 and the integral of C2, they match. a standard example, something like this. Let's look at the integral of, I don't know, how about y dx minus x dy over x squared plus y squared along the unit circle. Counterclockwise oriented, right? So line integral of that is what? I think I've worked this out before. X is equal to, x is cosine theta, y is sine theta. So then what? What's that?
Bottom half then cancels itself out.
Yeah, bottom half's just 1. And we're left with the integral from 0 to 2 pi. Let's see, y. So I guess I get minus sine squared theta minus cosine squared theta. I think I put a minus in from what I usually like to do. So I get minus 2 pi, right? So what's p equal to and what's q equal to here? P is y over x squared plus y squared, and q is minus x over x squared plus y squared. Let's calculate what's partial p partial, what's partial p partial y? I got to do what? Quotient rule, right? So I got 1 times x squared plus y squared minus 2 2y squared over x squared plus y squared squared. In other words, that's x squared minus y squared over x squared plus y squared squared. And, let's see here, partial q, partial x, it's partial x of minus x over x squared plus y squared, right? Which is going to give me minus, and then x squared plus y squared plus 2x squared divided by x squared plus y squared squared, which is x squared minus y squared over x squared plus y squared squared. What do you know? This vector field, p comma q, meets the condition of the deformation theorem, right? Before, I think we would have said, did I talk about closed forms in here? I can't remember. Did I define a closed form? Like mdx plus ndy being closed versus mdx plus ndy being exact? I think I did. So if we were to look at pdx plus qdy, this would show that form is closed. Anyway, the point is, py is equal to qx for xy not equal to 0, 0, right? I should be careful. I don't have that px is equal to qy at the origin. I don't have anything at the origin, right? It's not, this thing is not defined at the origin. So, I could ask you, calculate the integral around c of, y dx minus x dy over x squared plus y squared, right? And I could say c is this curve, counterclockwise oriented, and here's the unit circle, by the way. Because the vector field satisfies this py equals to qx condition between the curves, right, in here, all in here, we've satisfied the condition that's needed for the deformation theorem to apply, it follows that this integral, even though I haven't even described for you the formula for C, it can be anything, literally any curve, which just has, so-called winding number one. It just goes around once. It's a simple closed curve, a simple closed counterclockwise curve, which encloses the unit circle. Then is just going to give me back minus 2 pi again. That's the deformation theorem. Of course, you can go the other way too, right? You could look at a circle smaller. You could look at a smaller circle within the unit circle. You also have this closed condition in there. So in fact, you could shrink the unit circle all the way down to essentially like a really little tiny circle around the origin. You'd still get minus 2 pi. The source of this minus 2 pi has something to do with the origin. We understand that now from this deformation theorem, if you think about it. You could say the source of the minus 2 pi is the origin. Questions? What does this have to do with conservative vector fields? What was the one link in the chain that we haven't yet addressed? Is that the curl, remember, the curl of f equals to 0 on simply connected u, right, implies that what? F is conservative. I mean, you can pick any other, I don't know. Let's say, excuse me, I'll pick at implies that path independence. Let's go for loops. Integral around loops are 0. I kind of like that one. Remember, we had the 4 equivalent conditions. One of them was that the loops integrate to 0, and that's for all loops inside U, right? How does Green's theorem then help us with this? Now, I still can't do the 3-dimensional version. I can only prove it in 2 dimensions, but hey, 2 dimensions, not too bad. In 2 dimensions, basically this becomes, remember, the third component is just what? Qx minus py. That's the z component of the curl. If we look at the vector field f equals to pq0, so what? Excuse me. So let's look at the, assume that, py is equal to qx, or qx equal py, whatever you like, on simply connected. Subset of the plane. So let me just draw you a picture. Here's a picture of you. So what do? You can just take any old loop you like in here, right? Oh, I think I already did this some other day. I'm sorry, guys. I have a strong sense of deja vu right now. But if I take any loop, right, like this, then what is it? Say the loop is the boundary of some disk d inside the simply connected set. Then of course we have the integral around the boundary of d of p dx plus q dy is equal to the double integral over d of qx minus py, which is what? This is 0, but since you can do this for arbitrary closed disks inside the simply connected space, it follows that the integral around loops is 0 for arbitrary loops. Hence, the vector field has integral around all loops is going to 0, but we know that that then implies that the integral between, it has path independence as well, because we proved that if you have integral around loops, arbitrary loops being 0, you can trade that for path independence, and we then know that that also means that you can write it in terms of a potential energy function. Going back to that list of 4 things we had. Let's see here. So I want to show you guys something. I'm going to use the projector here if you don't mind. What would happen if you have more holes, by the way? What could you do?
One more pieces.
Right, just keep cutting it, right? If I had another hole like here, I just cut it again and again. And what ends up happening is then the boundary of D has what? The boundary of D has counterclockwise oriented this edge as well. And so then if you have a finite number of holes, you just keep adding clockwise integrals for the inside pieces. Or if you want to use counterclockwise oriented inside pieces, you have to subtract those. And you get a generalization of the deformation theorem that would say that the integral around the outer edge is equal to the integral around every single non-trivial loop integral that you can find inside. Every place that there's a singularity in the vector field, you might pick up a non-trivial integral. We had a singularity in the example we just looked at. There was a division by 0. That's where the non-trivial loop integral was coming from, right? So what I'm going to try to describe to you guys right now is the theory of electrostatics in 2 dimensions. So this actually would go in line with a 3-dimensional problem, which has kind of an infinite repeating story in all z. So if you have like the same thing happening at all z forever and ever and ever, then it's essentially a 2-dimensional problem because you can ignore the 3rd dimension. So this would describe problems like that. Like for example, if you every place I'm drawing a point charge in 2 dimensions, you could think about there being an infinite line charge going up out of the board. That would be the 3-dimensional problem to which this corresponded. But the question basically is something like this. If I have charge Q1, and if I have charge Q2, and so forth and so on, if I have, say, n charges, right, then if I pick some point, what's the electric field due to those charges in 2 dimensions? So the fundamental question is, what's the electric field due to 1 charge, right? So Gauss's law, well, I'm going to project here and try to write all this out. So one of the fundamental relations of, I do need my computer to project, don't I? One of the fundamental things in electrostatics, of course, is, Gauss's law. Gauss's law states what? It states that the reason that there's flux going out of a particular point, like this minus 2 pi that I just covered up, is that there's a charge there. There's a source for the flux, and that source is physical charge. This is Gauss's law. And Gauss's law further states that the only place that flux comes from is charge. So if you want to know where all the flux is, if you want to make a complete account for the flux that you find of the electric field through some curve, all you have to do is take into account where all the charge is. Once you know where all the charge is, you know where all the flux is. Once you know where all the flux is, then you can figure out the electric field at different points. Once you know the electric field at different points, then the force law is that if you put a little test charge there, the magnitude of the test charge times the electric field, well, that gives you the force on the test charge, and that's physics 232, okay? But I want you to see some of the math with me here now, if I can. Come on, where are we going? Oh, by the way, here's an example in the notes. Don't let me get too distracted by this, but here I apply Green's theorem with a hole to calculate the area between two ellipses. And of course, what you find is that it's the area of the outside ellipse minus the area of the elliptical hole inside, which is not too surprising, but there's an application of Green's theorem with a hole to a concrete problem. All right, we've done this another day, so I'm not belaboring it today. So two-dimensional electrostatics. The fundamental relation would be Gauss's law, that the flux is due to the charge enclosed through a specific curve. So I pick a particular simple closed curve in the plane. The flux through that curve should be proportional to the charge enclosed. Excuse me. So if I rewrite that in terms of our flux integral, it would look like this. Like the electric field dot the normal integrated over arc length should be equal to the charge enclosed. Now here, sigma is the charge per unit area, right? So if I integrate the charge per unit area over the area, that should give me the net charge in the region R. So then, if you think about this, right, imagine that there's a single charge Q inside a little region, right? If I then, apply Gauss's law there, what should I get? I should get the other rule is that charges are featureless, right? So the electric field that comes from a charge, it's the same in all different directions. Like it's not like, hey, I'm a charge, and I kind of like to put the electric field that way. Charges aren't like that. Charges are very boring. They put the electric field in all possible directions that they have to work with, provided that there's nothing else in consideration. If there's another charge there, then they kind of have to compete for where they can put the flux lines. But anyway, so that's why I have 2 pi r times E, because it's like that situation we looked at in the last class where we had the flux of the electric field lining up exactly with the normal direction to the curve, right? That radial vector field. We found that the flux was just the circumference of the circle times the magnitude. It's just like that. This has that same symmetry. And then, of course, the integral of the charge density over dA is just going to be Q. So this gives us, I'm applying Gauss's law. Gauss's law then derives for me the so-called Coulomb field in 2 dimensions. And Coulomb field in 2 dimensions says that the electric field drops off as the reciprocal of the radius. When you take Physics 232, this is in fact exactly the dependence you'll find for an infinite line charge, just like I was advertising. Of course, in 3 dimensions, the electric field drops off as the inverse square, just like Newton's universal law of gravitation, right? 1 over the radius squared is how the magnitude of the gravitational field drops off. Okay, so on the other hand, of course, I could calculate the flux of the Coulomb field by direct calculation, right? I can take the electric field, I can do this integral, right? And I get this, I get Q. Great, it checks. I calculated the flux of the Coulomb field, and I got back that the flux around the curve was equal to Q, which is what we said should happen. That's Gauss's law. Number of field lines depends on the amount of charge right there. All right, great. Now, of course, we could also calculate the divergence of the electric field. And if we were a glutton for punishment, we would do it like this, and we would find that it's 0. The divergence is 0 for this Coulomb field. That's also true in 3 dimensions. The divergence of the 3-dimensional Coulomb field is also 0. So then what? Well, then we could apply the divergence form of Green's theorem, right? And what do we get here? The flux is equal to the integral of the divergence, but hey, we just proved the divergence is 0, so we get that the flux on the one hand is Q, we calculated it directly right there, right? And on the other hand, it's 0. Oh man. Well, this is very troubling, because the charge shouldn't be 0 here. What's the deal? What's wrong? What's the mystery here? What you should have already learned from this example I did today about the minus 2 pi is that a single point can make a difference. A single point where your vector field is not defined can give you non-trivial integrals around loops centered about the point, because that single point may be where a charge is located, localized. And if that charge is localized at that point, flux can come from that point. And this divergence is 0 where it's defined, but where it's not defined is the origin. And the origin is where the flux is coming from. So we've glossed over the one point we cannot afford to gloss over. And in fact, of course, Green's theorem does not apply here because it's not a simply connected region. Because if you take a disk and you remove the center point, it's not simply connected. Green's theorem does not apply. There's no contradiction. We are simply using a tool we're not allowed to use at the moment. There is a fix for this in physics. So I told you how to resolve the paradox. Now I'm going to fix that a little bit, but now I discuss how to extend this for more charges. Basically, if you have more charges, you just add the Coulomb fields together by the principle of superposition. And so the net electric field will be the sum of the n electric fields at the different point charges. And blah, 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 blah. So the net electric field, if this curve C encloses the point charges, then we can use Green's theorem with holes to say that this integral is equal to the integral around the counterclockwise oriented little circles around the charges. So basically, I'm using this deformation theorem idea. Like here's a little circle around each charge, right? And if I have a big circle, then as long as these are counterclockwise, and as long as the divergence of the electric field is equal to 0 out here. By the way, the divergence of the electric field being 0 is another way of capturing the deformation theorem condition if you use the other version of Green's theorem. And then so I would get that the net flux around the big curve is simply the sum of the charge inside. So I mean, if you can do it for one charge, you can do it for n charges, all I'm saying. But how do we understand Green's theorem? How do we extend Green's theorem then in this physical context? The way it's done in physics typically is to introduce this thing called the Dirac delta function. What's a Dirac delta function, you ask? Well, I'm glad you asked. A Dirac delta function is this, well, it's not a function to start with. Just kind of disturbing terminology. But it satisfies this. The integral of the Dirac delta function, delta of r, what it does is it turns integration into evaluation. See, I integrate over dA. The only thing it cares about is just the value where the delta is 0. So that's the kind of thing we need in order to describe the charge density. Because where is the charge? The charge is at the origin, let's say, if we're just thinking about single point charge. And only there we have charge density. In fact, the charge density is infinite, but it's infinite in such a way that if we integrate it, we get a finite value of charge. And that's the idea of a point charge. So basically that's what I need. So when I integrate, if I say that the sigma, the charge density for a single point charge is just q times the Dirac delta function, if I integrate over a region R which contains the origin, I get back q. And more than that, you can in this world, you can prove that the divergence of R over R, which is, by the way, just basically R hat over R. This is up to a charge factor. This is the electric field in 2 dimensions. The divergence of the electric field in 2 dimensions is, in fact, 2 pi Dirac delta. So it wasn't 0. It wasn't really 0. It was 0 everywhere except for the origin where it's infinite. And it's infinite in such a way that when we integrate around the origin, we get something finite. So in other words, the divergence of E is q times delta of R. Then if you go back and you apply the generalized Green's theorem extended to the theory of distributions, we don't get q equals to 0. We get the flux is q for the same reasons it was before. And now the integral of the divergence is actually the integral of q times the Dirac delta function, which gives us back q again. Q is equal to q. Everything is fine and dandy as long as you don't have trouble with point charges being located at a point and having infinite charge density. If you don't like point charges being located at a point and having infinite charge density, you could imagine smearing them out and just always saying there's some like little tiny region where they're smeared out, and then you just have to work around that. But mathematically, since we can't observe that, it's kind of the same to work direct delta functions. Anyway, this is mathematics which is fairly new, maybe 1940s this was made rigorous. Dirac was a physicist in the early 20th century who introduced this idea, and we've been using them in physics and engineering since about 1930 or so, something like that. Thanks, guys. I guess now your weekend starts? No?